Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
Okay, problem number 4 here. So this is the last one that we're going to be going through in this video. So again, to start out, we'll start out with the MS or the mass spec data. So 132, this is our molecular weight. We know that we have 0 or even number of nitrogens based on this even number here, so that's our 100% abundance. Our 133, this is the M+1 peak, so we have 6.80% relative abundance. Divide that percent by 1.1% and we get 6.18, so we know that we have 6 or 7 carbon atoms again. And then if we look at our M+2 peak, we see that this is much less than 4%, so we know that we have no sulfur, no chlorine, and no bromine, unlike the last problem. So let's start out assuming that we have 6 carbon atoms. So our molecular weight, 132, minus 6 times 12, so minus 72, attributed to the carbons alone, leaves 60 AMU to be dished out to oxygen, nitrogen, and hydrogen. Now, this is much more complex than the previous problems, and so we're going to write this out in a table format. So we're going to list out all the possible different combinations for including oxygen, nitrogen, and hydrogen. So if we have 0 oxygens and 0 nitrogens, that means that we have 60 hydrogens. The formula is C6H60. This is impossible. What if we had 1 oxygen and 0 nitrogens? Then the number of hydrogens would be 44. Our molecular formula would be C6H44O. This is also impossible based on the total number of hydrogens relative to carbons. If instead we had 2 oxygens and 0 nitrogens, that would mean that we have 28 hydrogens with a molecular formula of C6H28O2. Still impossible. If we had 3 oxygens and 0 nitrogens, that would leave us with 12 hydrogens and a molecular formula of C6H12O3. This is a reasonable structure, so we'll keep that one for now. Another possibility would be that if we had 0 oxygens and 2 nitrogens, then we would have a total of 16 hydrogens, and we would have a molecular formula of this would be 32. So our molecular formula would be C6H32N2. Again, this violates the hydrogen rule. This is way too many hydrogens per carbon. If we had 1 oxygen and 2 nitrogens, that would mean that we would have 16 hydrogen atoms. Then we would have a molecular formula of C6H16ON2. Now, this is a reasonable formula, so we'll keep it. If we had 2 each oxygens and nitrogens, that would mean that we have 0 hydrogen atoms. Our molecular formula would be C6N2O2, also reasonable. Finally, if we had 0 oxygens, 4 nitrogens, that would mean that we would have only 4 hydrogen atoms and a molecular formula of C6H4N4, also a possibility. However, if we look at the IR spectra, we see a very prominent carbonyl stretch around 1743 wave numbers, and so we know that we have a C double bond O, and so we can eliminate the last possibility because there is no oxygen in this compound. We can also then look at the Proton Nmr Spectra. If we look at the integration, we have 1, 1.5, 1, 1, and 1.5 for the integrals. So when you add those up, you get 6 total hydrogens. And so what that means is that our molecular formula then must have some multiple of that. So the C6H12O3 would fit the bill, however C6H16O-N2 does not. And the fact that we have signals in an H-NMR spectrum means that we must have hydrogens, and so this one is eliminated. So what that means is that this up here is the molecular formula that we're going to be working with here. You can find that if you make a similar table, assuming that there were 7 carbons in the formula, none of the possibilities would be reasonable structures based on the combination of the IR and the H-NMR data that were given. We can then again calculate the degrees of unsaturation using the equation given in solving problem 1, and that comes out to just 1, so that means that we have 1 ring or 1 double bond in the molecule. Because we have the prominent C double bond O stretch here for the carbonyl group that we can guess that we probably use that there, so there shouldn't be any other double bonds in the molecule. Now let's look at the rest of the IR spectrum. There is no broad OH stretching peak attributed to an alcohol. We don't even need to bother looking for the NH stretching based on our molecular formula. There is no nitrogens. The degrees of unsaturations here is just 1, so we don't have a triple bond, but we don't see the terminal alkyne stretch in there anyway. Also, as confirmation, we don't see the peaks greater than 3,000 wave numbers attributed to the aryl or vinyl CH stretching, so no other double bonds in this compound. We do, however, see the alkyl CH stretches present, just lower than 3,000 wave numbers. And then again, because there is no OH stretch here, no broad peak, we know that even though we have 3 oxygens here, we do not have either an alcohol or a carboxylic acid. The carbonyl stretch here at 1743 indicates that we have either a ketone or an ester. And then that's pretty much all we can really gather outside of the fingerprint region of the spectrum. So now let's tackle the Proton Nmr data. So I already mentioned here we have the integral of 1, 1.5, 1, 1, and 1.5. And so if we want to get whole numbers here, and so you multiply each of those by 2, and you end up accounting for all 12 hydrogens in this molecule. So then let's go through these one at a time. For the peak at the chemical shift of 4.0 ppm, the integral of 1, I already said we multiplied that by 2, and so the total number of hydrogens that we have is 2. So now if we look at the possibilities, that could give rise to the splitting pattern of a triplet. It could be due to these 2 hydrogens attached to a carbon right next to another CH2 group. Or it could be due to these 2 hydrogens in between CHs on either side. That could also give rise to a triplet. However, usually in these situations, this top one, the first one that I suggest, is the most likely possibility. So let's move on to the peak at 3.9 ppm. So this is an integral of 1.5, so multiply that by 2, and so we get 3 hydrogens here. The most likely scenario is that we have a terminal CH3 group. If we then look at the one at 3.0 ppm, we have a singlet with an integral of 1, and so that means that we have, again, 2 hydrogens. And a singlet, just like this methyl group, means that it's not nearby any other hydrogen, and so there should be no other coupling. Meaning that this CH2 should be isolated from other carbons containing hydrogens. The peak at 1.3 ppm, sextet, integral of 1, so that means that we have 2 hydrogens again. Now, very similar to problem 3, based on the limited number of carbons that we have, we can go ahead and assume that this is due to the CH2 that is nestled in between a CH3 and a CH2. Those 5 nearby carbons, in addition to the one right here, will give rise to the sextet splitting. And then finally, at 0.9 ppms, we have 3 hydrogens based on the integral of 1.5, and then because it's a triplet and the fact that we're limited by the number of carbon atoms, this is the most likely possibility of a structural group that we have. And so these three hydrogens are these 3 on the end, the terminal CH3 group. Okay, so now let's take a step back here. We know from the degree of unsaturation and this large prominent peak in the IR spectrum that we have a carbonyl group. We have all of the hydrogens accounted for, all of the carbons accounted for, but we have 2 oxygen atoms unaccounted. And so let's go ahead and put all the pieces that we have together. Like I said, we have the carbonyl group, 2 oxygens unaccounted for, and then all of the other pieces that we identified from the Proton Nmr spectrum. So the coupling pattern suggests that we have a propyl group, so that's CH2, CH2, CH3. But that propyl group cannot be attached to OCH3 because this creates one whole molecule but leaves some pieces unused. The propyl group can't be attached to CH2 because the resulting structural piece would have a different H-NMR splitting pattern than what we see here. So this leaves the fact that our propyl group that we know we have is going to be attached to an oxygen atom or the carbonyl. So this leads us here to 3 final possible structures. Now we can use the chemical shift estimations to try to decide which out of these 3 is the best candidate, but it's probably beyond the scope of the current courses that you're taking. However, all 3 of these would be acceptable answers.